Okay guys, let's go ahead and we're going to talk about Vsepr theory and molecular shapes. Now, so far what we've looked at, we've done the Lewis structures and we figured out, hey, where do we put everything? But remember that when we do the Lewis structures, that we're writing that on a piece of paper and that atoms do not exist in 2 dimensions, that atoms exist in 3-dimensional space. So what we use Vsepr for is to determine the molecular geometry. Vsepr stands for valence shell electron pair repulsion. Okay, and it's the repulsion between pairs of electrons around an atom, and it causes them to be as far apart as possible. One thing that we have to remember is that all electrons are going to be negative, so they do not like each other because they're like charges. So basically what they do is they try to get as far away as possible from each other. Okay, and we use this Vsepr theory to predict the geometry of the molecule, the shape of the molecule. Now, the molecular shapes, that we have many different molecular shapes. Diatomic molecules, one thing that we can always say, remember our diatomics are Brinkelhoff, B-R-I-N-C-L-H-O-F. This is Brinkelhoff. Remember their diatomics, we always put 2's with them. Okay? Those guys will always be linear. Okay? Linear means that it's in a straight line. So if we have, we looked at nitrogen that was triple bonded to nitrogen, that guy is always going to be in a straight line. So it's going to look basically like a stick. It's just straight. Now, all other molecules can have different shapes based on the number of charged clouds around the central atom. Main thing here, make sure we circle charged clouds and make sure we're paying attention to just the central atom. We're not looking at anything else. We're looking at the charged clouds around the central atom. Now, charged clouds include bonding pairs and lone pairs. Now remember, we said the other day that bonding pairs are going to be our dashes. So when we're looking up here at our nitrogen, okay, these are going to be our bonding pairs. Those are our dashes. When we talk about lone pairs, those are going to be our dots. Okay, and it's going to be around the central atom. That's a key point. Now, if we have 2 charged clouds, okay, so we're looking at this, and no lone pairs, we're going to have a linear shape. Okay, when we're looking at this is carbon dioxide, and we see that around the central atom, we have to identify the central atom, which is carbon, we have 2 charged clouds. But basically these are bonded together, so we would not see that as dots. When we would draw it, it would look like this. So there's no lone pairs around carbon, so it's going to have a linear shape. Okay, if we have 3 charged clouds, okay, we did this one the other day, this is formaldehyde, and we look at it and we have 1, 2, 3 charged clouds. Okay, and you might be saying to yourself, well, that's a double bond. Does it count as 2 charged clouds? No, multiple bonds still only count as 1 charged cloud. So if I'm looking around carbon, I have 1, 2, 3 dashes. So it's 3 charged clouds. I don't have any dots around carbon, so therefore there's no lone pairs. It's going to be trigonal planar. If we look here at sulfur dioxide, I'm looking at it. Here's my central atom. I have 1, 2, 3 charged clouds, because remember charged clouds are the dashes and the dots, but here we have 2 bonding pairs and 1 lone pair. So what we would see is we have 1 lone pair. This would create the shape of bent. When we're looking here, if we have 4 charged clouds, we did this one the other day, it's ammonia. We see that we have 1, 2, 3, 4 charged clouds around nitrogen, and one of them is going to be a lone pair. So that will be trigonal pyramidal. Okay, if there's no lone pairs, like around CH4, which if we look at that, CH4 is carbon bonded to 4 hydrogens. it looks like this. Pretend there's another hydrogen down there. It has 1, 2, 3, 4 charged clouds, but doesn't have any dots around it, so it would be tetrahedral. Okay, if we look at it in water, here's water. We have 1, 2, 3, 4 charged clouds, and 2 of them are dots. And dots up here and dots down there. So if we have 2 lone pairs, it's going to be bent. Now with 5 charged clouds, guys, we're putting this on there so that you know and you can see these, because on your chart that you'll have, you will see a section for 5 charged clouds. We're not going to deal with those. We're just going to deal, the maximum amount of charged clouds that we can have is 4. We're not going to deal with anything more than that, because we didn't talk about anything, the other specific exceptions to the octet rule. So we're just going to be looking at only 4. But there are some elements that have 5 charged clouds, and we see that their shapes could be trigonal, bipyramidal. We can see seesaw shapes. And again, it's just writing those Lewis structures, but we didn't go over those. In the 5 charged clouds, if we have 2 lone pairs, we can see that it has a T shape and then a linear shape. And then they even have 6 charged clouds, which we have those shapes for 2 lone pairs, 1 lone pair, and no lone pairs. And we can see that they can have very different shapes. Now you might be saying, man, that's a lot of information. It's really hard to understand. How am I going to get this? Okay, what we use, and guys, we use this chart, and you'll get this chart on your test, so you'll have this to look at. Now, what we use is we only use up to 4 charged clouds. So we go ahead and you can just write through 5 charged clouds and write through 6 charged clouds, because we won't deal with those guys. We're just going to deal with these guys up here. Now, we can look over here, and you can see at the top left corner it says steric number. Okay, what this represents the charged clouds. Okay, 2 charged clouds, 3 charged clouds, 4 charged clouds, and so on. And then what you do is, after you figure out the charged clouds, you look at the lone pairs. Okay, so if I have 2 charged clouds, no lone pairs, I'm going to have a linear. 3 charged clouds, no lone pairs, I have trigonal planar. 3 charged clouds, 1 lone pair, I have bent or angular. 4 charged clouds, no lone pairs, tetrahedral. 4 charged clouds, 1 lone pair, trigonal pyramidal. And then lastly, 4 charged clouds, 2 lone pairs, I have bent or angular. Okay, and you can also see that it's going to give us this angle. Okay, this angle represents, this is our bond angle, it represents the distance between both of the atoms. So it's bonded to the central atom, and we can see that the bonds will be 120 degrees apart on trigonal planar. It'll be 180 degrees on something that's linear. It's going to be less than 120 degrees on bent or angular. So we're looking at this, and it gives us our bond angle as well. So there's a lot of information that we can use when we're looking at this chart, but you will get this chart on your test.